Today's lesson is on electricity and magnetism part 3. For odd periods, this is due on Monday, March 10th. For even periods, this is due on Tuesday, March 11th. Make sure that you take good notes for your quiz. So far, we've learned that electricity in the form of currents can actually create their own magnetic fields. For example, if we have a current going to the right, and remember my letter for current is I, we can use the right-hand rule to show the direction of the magnetic field. So at home, if your right thumb points in the direction of the current, the way that the fingers curl shows the way the magnetic field goes. Make sure you practice this. So my fingers curl from behind and up and over into the front. So this is eventually what my magnetic field is going to look like. Make sure you practice that so you know how to do this. So based on this idea, currents creating magnetic fields, a dude named Michael Faraday in the year 1831 decided that if magnetic fields can be created from currents, then why can't currents be created from magnetic fields? This whole idea is called electromagnetic induction. Our definition of electromagnetic induction is the process of creating a current by changing a magnetic field, Two important things that you should notice. This idea of induction means that something is actually caused. So in this case, we're causing a current to be made. And this idea of changing is also really important. The magnetic field, so B, must actually be changing in order for a current to occur. So if the magnetic field is at rest, then there should be no current that happens. And you'll see what I mean in a little bit. So we have 5 situations that we're going to talk about. In the first situation, the north pole of a magnet, so here's my north pole, will move into a coil of wire. So I'm going to draw my coil of wire kind of like this. All right, and remember that magnetic fields go away from the north pole of a wire. So we can see they're going away from the north pole. And again, I said that the velocity of the magnet should be going into the actual coil. However, the coil of wire was pretty happy exactly the way that it was, so it's going to react by trying to repel this field. Essentially, this wire creates its own imaginary magnet in which it has its own induced north pole that creates an opposing magnetic field. So here's my opposing magnetic field. We can see north and north, remember these will repel. Once this induced magnetic field, so this one right here is going to be our induced magnetic field, is created, this also creates its own current. And we can use the right-hand rule by having the thumb go with the induced magnetic field. So if my thumb goes in this direction, we can see here it is going from the right to the left. Point your right thumb from the right to the left. And then you have your fingers curling. We can kind of see how the induced magnetic field, the induced current will go from the front of the coil and then over and behind the coil. Okay, so that's the way that the current is induced. In our second situation, the only difference is that we're going to talk about the south pole moving into the coil of wire. So here's my south pole, and again, here's my current. So just so you know, this is going to be my front part, this will be my back part of the coil. And in this situation, remember that magnetic fields go into the south pole, But remember that we're going to be pushing this magnet into the coil of wire. So its velocity is going to be going into the coil. Now, same kind of thing, the coil was pretty happy the way that it already was, so it's going to react by trying to repel this field. So it itself is going to create an imaginary magnet where the south pole is repelling the magnet's south pole. And so its induced magnetic field will look like this. Remember that this induced magnetic field then creates an induced current. And again, let's have our right thumb go in this direction, so it's going to the right, our induced field. And once we do that, we should see that our magnetic field, our current that's being induced is going from behind, from the back of the coil, and into the front of the coil if we are doing the right-hand rule correctly. So now we want to start talking about what happens if a magnet leaves a coil of wire. In this case, we're going to start with the north pole of the magnet leaving. So here's our north pole, here's our coil of wire, this is the front, and then this is going to be the back right here. Remember that magnetic fields go away from the north pole, so this is the way the magnetic field goes. But in this case, the velocity of the magnet, we're going to be taking it out of the coil of wire. So this is going to be our velocity going to the left. And so this time, imagining our magnet was already in the coil of wire. The coil of wire just wants to be happy, doesn't want the magnetic field to leave, and so it's going to react by trying to be more attractive. It's going to try to attract the field back. So in this case, the magnet that's induced, the magnetic field that is induced, is going to actually have a south pole here because it's going to try to attract this field back. So remember, fields for south poles go into the south pole, magnetic field. And so this right here is going to be our induced magnetic field. Induced magnetic field is going to create an induced current. In this case, if my right thumb points to the right, my current is going to go from, the way my fingers curl, go from the back of the coil and goes over and into the front of the coil. Our last major situation is if a south pole of a magnet actually leaves the wire. So here's the front of my coil, here's the back of the coil. And remember that magnetic fields go towards the south pole of a magnet. And remember that in this case we're pulling the magnet out, so the velocity is leaving the coil. Again, the coil of wire just wants to be happy. It doesn't want this, because it started out with this magnet, it now doesn't want the magnet to leave, so it's going to react by trying to attract the field back. So it will essentially make its own magnetic field where it has a north pole here, because that north pole will try to attract the south pole. And remember that fields from a north pole will actually leave. So this is what our magnetic field will end up looking like, our induced magnetic field. So now, pointing our thumb to the left, as it has in our induced field, we can see that our fingers are going to curl from the front, kind of up and over to the back of our coil. So this is the way that the induced current will actually travel. So right here, letters A through D show the different situations we have for a moving magnet. We talked about if the north pole enters the coil of wire. We talked about if the south pole enters the coil of wire. We talked about if the north pole leaves the coil of wire. And we talked about if the south pole leaves the coil of wire. I should emphasize really quickly that an induced current depends on the speed at which the change in the magnetic field is happening. So if we've got, for example, the velocity of the magnet going in really quickly, then the induced current is going to also be much bigger. So I induced will end up being much greater. Same thing that if we have a really, really low velocity, so low velocity, then the induced current will also end up being very low. This kind of relates to this idea of if the magnetic field isn't changing at all, or if the magnet is at rest or stationary, then there's going to be absolutely no current. So this was our fifth situation, where if the magnet's not moving, then it doesn't matter, there is no current whatsoever. That's all for today. Make sure you practice all those situations so that you are ready for the quiz on Monday. Remember that all that matters when we're doing the right-hand rule is going to be the induced field in the coil. See you later.